Hi and welcome to my video about probabilities in Mendelian inheritance. The first thing we want to think about is a cross between two heterozygous individuals. Let's make a Punnett square. And remember, on the sides of the Punnett square, we put the gametes that each individual can make. And then we can fill in the square to reveal the genotypes of the possible offspring. So you can see in a cross between two heterozygotes or a monohybrid cross, we're going to end up with 1/4 of the offspring being homozygous dominant, half of the offspring being heterozygous, and 1/4 of the offspring being homozygous recessive. Let's do another fun cross between a heterozygous individual and a homozygous recessive individual. In this case, we'll make another Punnett square, put in the possible gametes that each parent can provide, and then outline what we'll see in the offspring. Here we'll get 50% are heterozygous and 50% are homozygous recessive. Next, I'd like us to remember the two rules of probability. We multiply when we're talking about two independent things. So this and this other event are occurring. And we'll add probabilities if we're talking about this or this other event happening. That's an additive probability. Now let's think about finding the probability for a dihybrid cross, or rather a two-gene cross. So here's the genotype of the first parent and the genotype of the second parent. And we want to find out what's the probability of getting this genotype, the double homozygous recessive, in the next generation. Well, we know from our Punnett square left that the probability of getting little a is 1/4. And, so we're going to multiply, the probability of getting little b is 1/2. So the probability of getting this genotype is 1/8. If we wanted to ask about the probability of getting this genotype, big A, little b, in the offspring, we could check the Punnett squares again and see 1/2 of the offspring will be heterozygous for big A, and 1/2 of the offspring will be homozygous recessive for B. So 1/4 of the offspring from this parental cross will produce big A, little b genotype. What this means is these two Punnett squares over here on the left are incredibly important, but also pretty easy to remember in your head. So I'd suggest learning to draw these Punnett squares by rote, or remembering the probabilities of offspring from each of these different types of crosses. These will be really useful when we're doing probabilities like this. Now let's do an enormous probability. We've got genotype big A, big B, little c, big D, big E. That individual is crossed with another individual who has all 5 of those same genes, but they're in a slightly different allele combination. So we did this cross and we looked at 1,024 offspring, let's say. I want to find out the probability of finding an A, B, B, C, C, D, D, E homozygous recessive individual. Well, if we consider the A cross, we know that the probability of finding little a is 1/2. If we look at the B cross, we know that the probability of finding little b is 1/4. The C cross looks just like the A cross, so that's going to be 1/2. The D cross also looks like C and A, so that's going to be 1/2. And then the E cross looks like the B cross, which is this top Punnett square up here, so the probability of finding little e is 1/4. we can multiply that together. So 2 times 4 is 8, times 2 is 16, times 2 is 32, times 4 is 128. So 1 out of 128 of the 1,024 offspring will have this genotype. We can actually convert that. So 1 individual out of 128 offspring. But we've actually got 1,024 offspring. So we can cross those out. That's going to be 8 individuals in the population of 124 total. So 8 individuals will have this genotype. Let's do that with another genotype. We want to find individuals that have the A, B, B, C, C, D, D, E, E, all heterozygous genotype. We can go back through our Punnett squares and figure out that each one of these has a 50% chance of coming up in the offspring. So that's 1 out of 32 individuals, or in the total population of 1,024 offspring, we'll actually have 32 individuals with this genotype. Now, somewhat more confusing is going to be to consider how many offspring have this genotype. At least one big A, at least one big B, little c, heterozygous D, homozygous recessive E. Now, remember that A bar, or at least one big A, is the same thing as the combination of how often we're going to say big A, and how often we're going to see heterozygous for A. So this would be an example of additive probability. The probability of finding this genotype is the probability of finding this plus the probability of finding that. So if we look at go back and look at our A Punnett square, that's actually the same as this bottom Punnett square here. Any that have big A's are going to be 50%, so this is 1/2. If we consider our B Punnett square, that's the same as this top Punnett square over here. We have the combination of big A, so 1/4 plus heterozygous, 1/4 plus 1/2, so that's actually times 1/4 plus 1/2. Or we could actually just write this as 3/4. 3/4 of the offspring will have a big B. And then we can complete the rest of this probability problem the same way we have been completing it. We'll get a 1/2 chance of little c. We'll have a 1/2 chance of big D, little d, and a 1/4 chance of homozygous recessive for E. So that gets us to a total of 3 out of 128 individuals, or 24 individuals overall in this population of 1,024 offspring. I hope you see that we don't need to draw out the probability of this enormous Punnett square each time we try and do a problem like this, but remembering the information from these super common smaller Punnett squares can help you calculate, using simple multiplication, each of the probabilities of a more complicated genetic inheritance problem. Please bring any questions you have to office hours or to class. Thank you.